Okay, thank you very much. Thanks for having me. This is a great occasion. I'm happy to be here, if virtually. Yeah, as Livia said, feel free to ask questions and interrupt me in any ways. There's a very big chance I'm not very familiar with Teams, so if you don't unmute yourself and speak, I may miss it. But you know, there's no malice in that. Just I'm very happy to discuss questions. So yeah, what I will tell you about today is sort of a first part of an ongoing project with Giulia Gugiatti. Everything I'll say has been done with her. The main objects that we propose to study in this project are these general surfaces in weighted projective space. In particular, we look at surfaces, this x 8k plus 4, a surface of degree 8k plus 4 inside this weighted projective space with weights 2, 2k plus 1, 2k plus 1, and 4k plus 1. This is a countable family of surfaces, but it turns out that they share a lot of properties between them. So I will often just drop the k from the notation and just denote x for any one of these surfaces. I'll make the k explicit when needed. So these surfaces here, they have singularities, which from the point of view of the derived category can give you a little bit of awkwardness, which we sort of bypass. There's deeper reasons to do this, and I'll mention them later, but it makes sense for us to look at the canonical stack associated with the surface. Which is essentially one way to attach. It's one way to resolve the surface, not by means of taking a resolution in classical algebraic geometry, but just attaching a smooth stack to it. So this will be smooth. And then what we are going to study about this stack is the derived category of coherent sheaves over it. So the main role in this talk will be played by this derived category. The reason why we look at this class of surfaces is sort of twofold. The first one is that this class of surfaces are interesting by themselves in that there's a paper by Jennifer Johnson and Johnson-Kollar that classifies, this is a lot of words, but I mean, it's a classification of essentially mildly singular del Pezzo surfaces. Let me tell you just very briefly what all the words in here mean. So these, except for a series of sporadic examples, this series is just all of the quasi-smooth and well-formed anticanonical log del Pezzo surfaces. The way I think about these words is that if I have something that is quasi-smooth and well-formed, my stack associated to it will be smooth and an orbifold. Depending on how you think about this, orbifold may imply smooth, but by orbifold I mean that the stabilizers are just in codimension 2, so they're supported on points. An anticanonical surface will mean that its canonical bundle is linearly equivalent to the O of 1 coming from the projective space that they're embedded with, so that the anticanonical is very ample without taking multiples. And the log over here, I mean, this is a condition on singularities. Essentially, this says that their singularities are cyclic quotients. So they are singular, but they're somewhat very nice. The canonical stacks associated to them are very nice. And they represent almost all of the surfaces with these properties. Another reason to look at these, and the main motivation for our project, is to do homological mirror symmetry for these surfaces. There's one aspect of them which makes them interesting examples from the mirror symmetry perspective, is that their anticanonical series is empty, because as you can see, O of 1 has no sections in this weighted projective space because the weights are all bigger than 1. But if the anticanonical series empty, that means that there's no toric degeneration to these surfaces, because that would give us an anticanonical divisor essentially. So this means that there's no way to run the intrinsic mirror symmetry machinery. I'm referring to the Gross-Seibert approach. So that's not applicable to these surfaces. However, the mirrors for these surfaces are known. They've been constructed by Alessio Corti and Giulia Gugiatti. The construction is well, it's not one of the classical construction. It's something new. The Hori-Vafa method doesn't work. Berglund-Hubsch doesn't quite. It's not applicable to these. Their construction is quite arithmetic in some sense. They start from a hypergeometric series. But our future goal is, since the mirror is known, to prove an equivalence between this category of coherent sheaves. And I'll be sloppy with the notation here, and I'll just write the Fukaya category of X check. If you're familiar with these topics, you know that there's an awful lot more that comes into even stating this. This category here is not quite a trivial object to even define. I just mean that there should be some symplectic data on the mirror that should match up with what we find by studying the derived category of these stacks over here. And that's another reason why one would want to look at the stack. What has happened in the past, for example, there's some papers by Oruka, Tsarkov, and Orlov that do homological mirror symmetry for the Pezzo surfaces or weighted projective planes. It turns out that the right statements involve, well, the statements that work involve the stack associated to the surfaces. So that's another reason why we would want to look at the stack. And here's a main theorem. We just show, essentially what we do in this first part of the project is to construct full exceptional collections on the derived category of the stack. Let me just remind you very briefly what an exceptional collection is. Essentially, a triangulated category admitting an exceptional collection means that it decomposes into relatively simple blocks. And all the information of the derived category is in the gluing of these blocks with one another. So yeah, I'll just remind you, an object is exceptional if the only self-maps are scalar multiples of the identity. And when I put a little bullet on top of my HOMs, I mean that I really do mean that there are no x1s, no x2s. I want to encompass all of the HOMs from E to E shifted by something. And then once you have an exceptional object, you can define an exceptional collection, which is a little bit more than just a collection of exceptional objects. So it is a collection of exceptional objects such that there are no maps in any degree going sort of backwards in these collections. So I guess I should write that the HOM bullet between EI and EJ is 0 for every I bigger than J in this indexing that I chose. And it is, I mean, this would be less of a theorem if I omitted the word full. A full exceptional collection is essentially a collection that spans the derived category. I guess technically this means that the smallest triangulated category containing the EI is the whole category, in this case, just dp cox. So yeah, I'll just mention this corollary here, and then maybe I'll take a brief pause if there are any questions. A byproduct of the existence of these exceptional collections tells us that we can actually express the derived category of the stack as the derived category of modules over a certain algebra here. I guess I should say that in general, when you have an exceptional collection, you can make this into a DG algebra. But because of how collections look like, we can in fact make lambda into a honest algebra. So I guess a DG algebra concentrating degree 0. And this is sort of the foundation to prove homological mirror symmetry, or at least in the cases that are already known. What you do is you find this algebra and then you cook up another algebra from the symplectic geometry perspective, and then you sort of stare at them long enough until you realize that they're isomorphic. Yeah, so, but it is, so hopefully I can convince you that it is important not only that exceptional collections exist, but that we need to really understand them very explicitly to be able to grasp and to describe these algebras lambda, which are the ones that ultimately will give us, hopefully, sometime in the future, the result that we're aiming at. Are there any questions? Is it making good sense so far?
Franco. Hi, this is Tyler.
Hi.
Do you get strongness in your corollary or do you not?
We only get strongness for k equals 1. We've been struggling with strongness a long time, but we're not able to do it. However, we only get homs and ext1s, which means that you could theoretically just run some sort of universal extension trick, and you still get it's a bigger algebra, but it's as if it was strong. You get a tilting complex at the end.
Okay, great. Great,
Yeah.
That answers my question. Thank you.
Mm-hmm. Okay, so yeah, I guess I'll spend most of the rest of my time telling you how we cook up these decompositions and these exceptional collections. The starting point, and maybe the main technical ingredient that we use, is the GL2 McKay correspondence. What happens in our case is that our singularities are they are all cyclic quotients, as I mentioned before, which means that the groups acting locally are just finite small subgroups, cyclic subgroups of GL2. And if you've heard about the McKay correspondence before, you probably know that if these groups acted with determinant 1, meaning they're actually subgroups of SL2, then the singularities would be Gorenstein, which means that the derived category of the stack would be equivalent to that of the minimal resolution. That's not the case here. The singularities are not Gorenstein, and all we get is a fully faithful functor from the derived category of the minimal resolution to the derived category of the stack. The orthogonal complement of that, this E1 through En, this is an exceptional collection. And the initials that I put here are Ishis and Uedas. Because they're the ones that construct these exceptional collections that I'll tell you a little bit more about it later. This comes from the singularity data of the surface X. And then, yeah, so for the rest of the talk, I'll sort of subdivide it into pieces that will tell you a little bit about either one of these chunks over here. And then there's an extra hidden piece, which actually kept us pretty busy, which is if we want this to be explicit, it's not enough to just work out what the objects are, but we need to figure out what the maps are between them. And maps that are not trivial to compute are maps that go from one of these exceptional objects to the derived category of the stack. So anything in the image of that functor. So these are going to be the three main chunks of the rest of the talk. Did I close enough parentheses? Maybe I closed too many parentheses. Oh well. Okay, let me start with the minimal resolution. I'll tell you a little bit about the singularities of the surface. There's 5 singular points. One of them has a group acting of the form 1 over 4k plus 1, 1, 1. If you're not familiar with this notation, by this I mean the group generated by a k plus first root of unity acting diagonally, or k plus 1 equals 1. Yeah, that's just what it is. The group acting on these other 4 singular points is a group acting by 2k plus first roots of unity, but now the weights are slightly different. So I'll be acting with, I guess I'll call it C, whatever I can generate by a primitive 2k plus first root of unity, acting with weights 1 and k. Yeah, so those are the singularities that we have to resolve. If you've seen some cyclic singularities before, you know that there's a nice combinatorial picture going on here. You can take the continued fraction of 4k plus 1 over 1 and 2k plus 1 over k in both cases, and that tells you essentially the dual graph and the self-intersection of the exceptional curves. So patching that together, you get this theorem, which is stated in the form of a picture. There's a little bit more than the picture, and I'll comment on that later. But essentially, the minimal resolution looks like this. You start with our surface X down here. There's this configuration on X for which you sort of have the 4 singular points P1 through P4. They lie on a line, and they're all connected to the 5th singular point through lines inside X. So when you start blowing up, the configuration of curves looks sort of like this intermediate step that I sketched here. The first blow up you want to do is to resolve the point at X. That only has one exceptional curve, this red curve I extracted here. And then you start blowing up the other singular points P1 through P4. What you end up with is the initial lines, the blue lines over here. I think, yeah, you can see the cursor. Okay, I'm not just talking to myself. The blue lines over here, they were 1 curves, but they met 2 blow-ups, so they are now -1 curves up in this picture. And all the exceptional curves you extract were regulated by this continued fraction arithmetic. They're all -2 curves, except for the last ones, which are -3 curves. They're highlighted in pink up here. So that's our minimal resolution. That's how it looks like. However, when you start staring at it, you may want to look for a minimal model for this, which means you're tempted to contract the -1 curves. If you do that, you see if I contract this -1 curve, I will make the first one of the -2 curves into a -1 curve as well. So I can sort of cascade down to consecutive constructions of this sort. So I guess what I should maybe write down is that this map that I drew here, this tau map, factors through all the minimal resolutions for lower values of k. So they're sort of nested up. And that's why it's convenient to just treat all the k's in one fell swoop, because they all boil down to the same surface down here, this x2, which turns out to be a del Pezzo surface of degree 2. And it's not just any one of these. As you can see from the picture, you end up with a Del Pezzo surface where four lines, 4 minus 1 curves meet exactly at one point. Not every Del Pezzo surface admits such a configuration. A point that satisfies this property is called a generalized Eckert point. Eckert points were classically introduced in the study of cubic surfaces, which are Del Pezzo surfaces of degree 3. In that case, an Eckert point is just a point where 3 of the 27 lines meet. A generalized one is one where 4 of the 56 lines of a Del Pezzo surface meet. I'll come back to this because it will be important for explicitly describing our exceptional collection. Okay, so I gave you the picture, and hopefully that convinces you that that's how the minimal resolution works. However, we're interested in doing a little bit more than that, and we can actually sort of work out this picture by keeping track of equations, because we can just do it by taking a star subdivision of the ambient projective space. So I guess something that I haven't mentioned before, but I should, these x's are not toric varieties. They are hypersurfaces in toric varieties. So toric geometry helps, but you have to do some yoga to make it helpful. And that's exactly what we did here. By keeping track of equations in our star subdivision, we get essentially the following thing. If my x was defined by a certain polynomial of degree 8k plus 4, so it depends on this parameter k. Yeah, so I fix that polynomial, I fix its coefficients, and then the parameter k will vary. The result of, I mean, what we get out of this theorem is that x2, our Del Pezzo surface, is actually determined by the same polynomial when I plug in a 0 for all the k's. So the sort of the coefficients defining these polynomials are uniquely determined once you start with x, also for x2, which gives us this nice corollary that tells us that if I look at the moduli space of all of these surfaces of a given degree for k plus 8, then that moduli space is birational to that of Del Pezzo surfaces with an Eckert point, which is I guess it's a codimension 2 locus, a 4-dimensional locus inside the moduli space of Del Pezzo surfaces. Yeah, and in particular, all of the moduli spaces of these surfaces are birational to one another, independent. That, well, I mean, as k varies. Okay. Another corollary of this construction is the existence of an exceptional collection for the minimal resolution, which, if you recall what was written before, by itself proves the existence for the whole thing, because the derived category of the stack had the, well, I'm getting ahead of myself. We'll come back to that. Why is there a full exceptional collection on the minimal resolution? Is due to this blow-up formula developed by Orlov. Essentially, what we've done here is to write the minimal resolution x twiddle as a repeated blow-up of a Del Pezzo surface, which, if you are familiar with your classical geometry, know that that is a blow-up of P2 in 7 points in general position. So what we did was to start from a variety P2 that has an exceptional collection and repeatedly blow up, which by Orlov's formula tells you that you get, well, in general, you just get a semi-orthogonal decomposition, but you can just pull back the exceptional collection and add one extra piece, one extra exceptional object at every step of your blowups. So that gives you the existence of an exceptional collection on the minimum resolution. However, I just want to comment on something on this formula. The formula tells you that whenever you blow up a point, the new object showing up is the structure sheaf of the exceptional divisor. So if I were to repeat blowups, I get a much messier picture if I keep blowing up points that are on exceptional divisors of previous blowups. Which is, I mean, you don't need to go to derived categories to know that. Blowing up separate points is easier than blowing up one and then blowing up another point on the same curve. So the reason why I'm telling you this is that I want to give you a more explicit version of this corollary, this second corollary here. But to do that, we're going to need to dive a little bit further into how x2 is a blow-up of P2 in 7 points. So let me remind you of a few classical facts of the Pezzo surfaces, and then I'll tell you how we decided to use those to make our collections as nice as possible. The anticanonical series on a del Pezzo surface maps it 2-to-1 to P2. And the cover branches over a quartic curve that admits 28 bitangents. If you look at the pre-image of each one of these bitangents, is just a reducible curve with 2 components, and each component is a line on x2. And by a line on x2, I just mean a -1 smooth -1 curve. Which I guess, if I just say that, it also implies that it's rational. Yeah, so that's one point of view you can take from this del Pezzo surfaces. But as I mentioned before, you can also write them as blowups of P2 in 7 points in general position. The way you can do that varies. So you have many choices. In particular, for any 7 disjoint lines on your x2, you can decide to contract those, and that will give you one different map to P2. Yeah. So the way we decided to use that to describe our collections is essentially the following. As I mentioned, things get awkward when your blowups are centered at points that are on exceptional loci of previous blowups. So what I would like to have, and what we managed to arrange, is that, so what we want is that the set of exceptional curves that I get from my first blowup from P2 to X2 does not meet these 4 purple lines that go through the generalized Eckert point. C10, C14. Yeah. In other words, my next blowup will be Q. I don't want any one of the lines passing through Q to be one of the exceptional lines coming from the blowup of P2. And it turns out that this can always be arranged. And it's a very lattice theoretic argument. And by that, I mean that Magma did it for us. The Picard group of a del Pezzo surface is very well known. It's a lattice. And so you can just write down the classes of these curves in the lattice. You sort of classify the sets of 7 disjoint lines, and you just check that you can always pick one whenever you have 4 lines that meet at a point. Okay, so that gives us this formulation of corollary 2 that is more explicit. It's not just any exceptional collections. We can build an exceptional collections that look like this. First of all, you have the pullback from P2. That's going to consist of 3 exceptional objects. So that's this piece over here. Then the blow up from P2 to that Pezzo surface will give you these 7 exceptional objects here. The next sort of, well, I mean, the blow up of the generalized Eckart point will extract a sheaf like this, which turns out to be one of the most complicated objects in this sequence. And then you'll have these 4 blocks over here that correspond to the 4 chains of rational curves. I'll just go back up here, that you can see in this picture. So there's the point Q will give us something that is supported on F, and then we'll get something that is supported on each one of these chains. Okay, every block in fact looks like this. The objects here are just sums. Well, they're subchains in the chain of exceptional objects. Just to give you an idea of why this exceptional sequence looks like this, we can go through a couple of the blowups that one needs to keep track of. If you start from your Pezzo surface, you have the exceptional objects O of Li. Then you blow up the point Q, that will extract one exceptional divisor in the form of the structure sheaf of F. When you blow up again, you're supposed to pull back F, but that means that it will pick up one copy of the new exceptional divisors, these new red curves that I'm picking up here. Those are exceptionals of the new blowups, and in fact, they'll show up in this F thingy. And Orlov's formula will give you 4 new exceptional objects here. You blow up again, you blow up these points, Some among those points. There has to be a way to figure it out, but if I do it on the fly, I'll get it wrong. It's 50-50, but I get it wrong. But yeah, when you blow up again, you're supposed to pull back this divisor now, which will pick up, yeah, you're blowing up these points, right? It will pick up the new exceptional curves here, and it will pick it up twice. So that's going to be the new summon there. And all of the other exceptional objects, they will also pick up new curves, and that's, so this part over here is how you get the blocks BI that are orthogonal to one another. Okay. Any questions so far?
There are no questions on the chat for now, so.
Okay, so far so good. Yeah, so this is pretty much what we do on the side of the minimum resolution. I'll just very briefly move to the stack. There's a lot to be said there, but it's not our work. It was mostly done for us before. What happens on the stack is that there's going to be these 5 other blocks, 1 for every singular point. And in every block, there's exceptional objects that are very simple, and they're quite literally simple. They're simple sheaves. They're skyscrapers at the singular point, together with a different equivariant structure. So what you want to do here, the recipe to cook up these blocks, is to look at the non-special representations of the group G. Can talk about what those are, but they're essentially the representations that are disregarded by the minimum resolution, almost definitionally. Well, no, it's not definition, but yeah, they don't show up in the minimum resolution. They show up here, and Ishii and Ueda tell us how to assemble these into an exceptional collection. So every block looks like skyscraper with different equivariant structures. There's I guess 4k-1 elements for the special singular point, and for the 4 other singular points, they're just k of them. The way you compute maps between these is actually regulated by a quiver. It's called the McKay quiver of the singularity, and yeah, it's a very combinatorial object, but it boils down to Schur's lemma. It boils down to the fact that to compute a space like this, you just have to essentially count multiplicities of sigma inside rho, or maybe inside a resolution of rho if you want to do higher maps. But very fundamentally, this follows from Schur's lemma. So I'm not going to say much more on that. The home spaces there, they're sort of given to us. It is interesting that they line up nicely, and we only, if you shift these objects accordingly, you only get homes and X1s, which is somewhat surprising. But the last thing that I would like to comment on is how we understand maps from these exceptional blocks that come from the exceptional collection, that come from the singularities and the McKay correspondence to the derived category of the minimal resolution. The way we do this is, well, we can write down explicitly what a left adjoint functor to our functor phi is. And that's just phi is a functor of Fourier-Mukai form. So it's not hard. You sort of compose the adjoints of each one of the ones that make it up. And then we do the computation. So we send these exceptional little bricks over to the surface, and then we do computations on the smooth surface. I guess I don't know if you think that this approach is natural, but I think it's convincing to put in the effort and just try to work out the adjoint here, because it makes these computations much more general. So the computation of the left adjoint does not depend on the geometry of this X tilde. So the other way that you could approach this problem is, I have an exceptional collection on X tilde, I apply phi, and then that gives me objects on the stack, and I compute there. Computing the adjoint means that this machinery applies to any surface with this type of singularity, not just the ones that we just studied. Yeah, so we compute, and I mean, another thing that makes this simpler is that the adjoint, we only need to compute it on skyscraper sheaves tensored with a representation. You can do that in two ways. There's one sort of more explicit approach, which uses toric geometry, just resolving torically the singularity. Or you can sort of follow the trace of Ishii. I don't want to risk a year. In which you can use this, they're called Auslander-Reiten sequences, which are some sort of representation theoretic tools, but the result you get at the end is very similar. One thing that I should comment on is that once you do this computation, so you look at what the image of this psi of OP tensor rho is, and there typically will be sheaves supported on one of these exceptional curves that I pictured down here. Well, not this one, let's start from here. Something interesting that happens is that when you compute the highest, the last representation of the PI points, you get something that is supported on this last curve. And these pink curves over here are curves that survive all the way down to P2. So all of the others, the blue ones here, they get contracted when you go down to P2. So computing their maps to and from them is relatively easy, because it's sort of a projection formula trickery. You just push it down to P2, that's a point, we know maps to skyscraper sheaves. With these pink ones, you don't know what their image in P2 is. And in fact, depending on this map pi, it can be very different things. Well, it can be different things. They're all very different. It's not wild. But one thing that we need to do to write these exceptional collections explicitly is to actually control the image of these points over here. And that, as a byproduct of that, we get this nice little classification of generalized Ecker points. So the question that we wanted to answer here was, I have the Pezzo surface, so it is in some sense the blow up of P2 at 7 points in general position. How do the points need to look like for me to be guaranteed to have a generalized Eckart point under the Pezzo surface? So what are the possible configurations of x1 and x7 in P2 such that if I blow them up, the surface will have a generalized Eckart point? And it turns out that there's only 3 possibilities. Well, it's really 5, but you can always look at the dual configuration. I mean, the map is 2 to 1. So I'll say a little bit more about this later, but there's essentially 3. And among these 3, we'll look at them in more detail in a second. But there's only one of them that does not contract any of the 4 lines that give up the generalized Eckart point. In fact, well, let's focus for a second on this picture here. If I have a configuration like this in P2, so I get 2 lines and 2 conics meeting at a point, and then I blow up all of the intersection points between the lines and the conics, except for the point where they all meet. So I'm not blowing this point up, but I blow up all the others. That will give me the Pezzo surface with a generalized Eckart point. Yeah, well, you can think of it like this. If I have a line in P2 and then I blow up 2 points, that will become a -1 curve. If I have a conic in P2 and I blow up 5 points on it, the conic is a 4 curve, so it will become a -1 curve. And that's essentially almost the only way to get lines on the Pezzo surface, by blowing up 2 points on the line or 5 on a conic. This configuration here allows you to do exactly that for 2 lines and 2 conics. So when you blow them up, you get your Eckart point over here. Another possibility is the second one. This time I have 3 conics that all have the same tangent direction at a given point down here. And what I want to blow up are the intersection points of these conics. When I do that, the exceptional divisor here will become a line that meets the 3 conics, which will become lines because I blow up 5 points on each of them. And that will give me an Eckart point. The difference is, to realize this configuration, I have to contract one of the lines inside my Eckart point. Similarly, to get this other configuration here, this is a line, a conic, and a cubic with prescribed tangencies here at this point down here. In this case as well, the 4th line giving me the Eckart point is the exceptional divisor at this point over here. So if you're starting to see a pattern in our talk, our main goal here and what we would like is to always be able to arrange a situation like the first one, because we don't like blowing up points on things that were exceptional in previous blow-ups. It turns out that you can always arrange this. This is also a lattice theoretic argument and a computer algebra computation. By doing that, well, now we have controlled the image of those pink curves inside P2. We know that 2 of them will be lines and 2 of them will be conics. And that allows us to finish the computation of the Helm spaces between objects in our exceptional collection. Okay, let me just mention, I guess I went a little bit faster than I was expecting. I'll just mention some future directions of things that we would like to do with this machinery. I guess the first natural next step is to start looking at the mirror of these objects. The mirror, as I mentioned before, the mirror doesn't quite fit into the intrinsic mirror symmetry program, but it doesn't have a QG degeneration, but it still is a Landau-Ginzburg model. The potential is just not a Laurent polynomial, but you can still theoretically talk about vanishing cycles. And once you have vanishing cycles, then you're sort of all set to define a Fukaya category. And the Fukaya category will presumably have some exceptional objects. This is just a lengthy computation and a quite difficult one that we want to do, but we've just started. At the end of which, we should be able to find an algebra that looks like the algebra that we just cooked up on this side of the mirror. So that's what's on the plate for us in the near future. Other things that we would like to do with this is, well, this is not the only class of surfaces for which mirror symmetry has been established in some way, but not from the homological mirror symmetry point of view. So especially the computation of this adjoint functor may help you. It will give you new ways of understanding the derived category of this sort of smooth stack attached to mildly singular surfaces. And I guess something that brings me back to what I was doing during my PhD is that when I give you an exceptional collection and you get one of these algebras, that also gives what's called the heart of a bounded T structure on the derived category, which opens the door to some stability conditions problems. The stability manifold is also a mirror symmetric object in some sense. It's quite hard to unpack, like to get a precise statement of what the sense is, but it would be nice for this to hold for more than the surfaces that are known now, which are essentially projective space and K3 surfaces and some other few examples. So these are possible longer term applications of this result. Okay, I'm a bit early, but let me just stop here and maybe pause for one last round of questions.